Okay, so what I want us to do on, we were working on exercises, on exercise 3, and I asked you to do, to complete exercise 3 with regards to the calculations. And then I asked you to do exercise 4. Now, I reviewed what you guys did, and I just have some observations. In the case of exercise 3, we had already identified the procedure to get the total capacitance. And we identified which capacitors were going to be grouped in series and in parallel. What I'm going to show here, this is the procedure. It's the same procedure, but courtesy of House Angels. It's the same procedure with the calculations. Okay. One of the mistakes I noted, just for you guys to be careful, and I think a few guys made this mistake. It was actually in this calculation here. So capacitor 1 and 2 come out of this combination, right? Yeah. And then this gives us capacitor 1 and 2. And then you notice that we have 3 capacitors in series.
Yes.
So the series has to be the calculation of the 3 capacitors. So what I noticed in some cases is that you just grabbed 2 of them for the calculation. In some cases, I'm not saying that I don't remember exactly which teams did what. But in some cases, the 3 of them were considered either here or here. Okay. That was, I think, the only thing I observed in the calculation. So I'm leaving here on the PowerPoint the procedure based on what this house did, and just for you guys, for the rest of you, to just verify the calculations. Again, the procedure was correct, but that was the only thing I noticed, that in some cases, instead of grabbing the 3 to do the calculations, some of you just grabbed 2. So and so that was the only detail. Okay, so that I noticed with that one. Now with number 4, there was another thing that happened here, and that's why I want to solve number 4 here, because there was one small detail that I noticed in the procedures that has to do with interpretation that I think we should go through it here, because it's important when we actually build circuits to understand that. Yes.
I have a question on number 3.
Yes, go ahead.
Is the answer correct? Is it the answer?
I believe it is. I believe it is.
I think it's wrong. It's 1.6 minutes. 0 times 10 to the minus 6. Yes, see, this one. I think she just got confused because she tried. No, it's because she got it, but then she copied another one. So
I think maybe I grabbed the screens. I'm sorry, I did the screenshot, so maybe I copy pasted something here incorrectly. So it's this one, right? Yeah, I copy pasted.
Yes, because you put that it was a series, and there is a series.
1, 2, 3. Yeah, it's this one over here. I copy pasted it incorrectly. Yeah, I'm gonna correct that. Yeah, it should be 1 microfarad if I'm not mistaken. Yeah, it's the. Yeah, I was trying to put everything on the same screen, so I cut some things and I pasted them. I'm gonna correct that, and that's gonna be in the next version of the PowerPoint I'm gonna upload today. Now, one thing here with this one, I want to do the same procedure as the other one before we do the calculations, just to go step by step how we need to interpret the parallels in the series. One thing that's very important, very, very important for these circuits, because we're also going to be seeing circuits in learning module 3 and 4, is the connections, and in the case of equivalence, where we are being asked to do the equivalence. So notice that there are these 2 lines here in the circuit. These 2 lines represent, that's where I'm trying to measure the equivalent capacity. Or in other words, if I were to have the device and have the two terminals, the black and the red terminal that we were talking about, this is where I would put it to measure. Now, it's actually the measurement of the capacitance can be different depending on where I'm placed. So we always have to keep in mind the lines, okay, when we're doing them. And so let me go through the steps and mention where I noticed that,
So we need to finish everything in that assembly. To measure everything.
yeah, so we're imagining that we're measuring it there. Now, I'm not, that's why I want to do it here because I'm not considering it that you necessarily did it incorrectly, but it's something that we didn't stress or point out. We did in the previous exercises, but let's do it here. Let me just check the color coding that I used on the previous one. So it's blue, orange. Okay, so I'm gonna first name the capacitors with a certain naming structure. You could have done it differently, but in the end, the steps should be similar. So I'm going to say that this one is C1. I'm going to say that this one is C2, C3, C4, C5, and C6. Okay, just to name them. And I'm going to follow the procedure in certain steps. There's more than one way to approach them because there are certain elements that are clearly in series or clearly in parallel. We could focus on one or the other first. What I'm going to do right now is that I'm going to focus first on this one. These two here. It's like the sneeze was there and then the professor made the sneeze go away. I'm sorry, I wanted to ask a question. I'm sorry. No, it'll come back. I'm sorry. Go ahead. Yes.
Do we have it wrong, that one?
I don't remember. I think so.
Yes, right?
I think so, but again, just to be clear, it's not a wrong that, it's a wrong that I want to solve it here because that clarification about the lines is important. So I'm not saying it, if I were to remove these lines and not put them here, then we could really interpret however we're measuring the capacitance. And so technically the procedure would be correct. So I just want to solve it here so you understand this part, okay? Because otherwise, most of the interpretations you made about series and parallel will be actually correct. Okay, so the first, I'm going to take these two, and we know that these two are series, right? And I'm going to call that capacitor 1, 2. And so we're going to have this here. And I'm going to keep the line here. And so this one is going to be called capacitor 1, 2. We've still got capacitor 3, capacitor 4, capacitor 5, and capacitor 6. Okay. Now there's a couple of ways we can approach this. I'm gonna join these two. These two are clearly in. What is this connection here? Parallel. Okay. And so I'm going to redraw this, and I'm going to have one capacitor here. I'm going to call this one C123. This is C4.
I have a question.
Yes, go ahead, Ian.
What if the C1, C1, 2, 3, we would have left it in the other side.
In which other side? Even?
Like
She's talking about the two
C1,
lines.
C1, 2, where that one is.
So C1 to this one?
Like this. Like this.
Oh, that is the medio. Yes, ese 1, 2, 3.
Instead of putting it here,
Como poner 1, 2, 3
Oh.
aquí.
Okay, okay. So from what I'm seeing that you're drawing there, I'm just gonna draw it here on the bottom to see if I, this is a note. What you're asking is that you put it something like this, C1, 2, 3, and then you do this, like that? And then the rest is over here, right? Okay. Okay, so what this would be incorrect because of the following. Once we join these two, we're creating another element, which is this one. If you put this line here, you are literally putting another element here in the middle. And this connection here, this is a short circuit. This is basically, I'm gonna ask this. This element and this element, how are they connected? In parallel. And this element is nothing, right? So if I put these together and this is in parallel, I'm creating a connection where I'm literally eliminating this here. Okay, so once you join them, you're either joining them, because I do understand kind of the reasoning. You're saying I'm joining it to the left or I'm joining it to the right. Either way, you're merging them. Okay, so if you merge them to the left, you're just left with this one alone. If you merge them to the right, you're still just left with one. Okay, it's very important to not. And it's going to be even more important next learning module when we're talking about resistance. It's very important to not create connections where there's no element where there wasn't there before. Okay, because electrically this is what's called a short circuit. Okay, you've heard the term short circuit before, and you know that short circuits aren't good. Basically, a short circuit is that I'm connecting two terminals together, and that's usually not something good for any element. Okay. Is that clear? Okay. Now from here, what I'm going to do is the following. Because of the line that I'm putting there on the middle, and this is where maybe some of the confusion was generated. What I saw, I think, in some cases is that when you guys redrew the circuit, these lines weren't there. And so if that was the case, then it's very clear to say, oh, these are in series, right? So I saw that in some cases, but since there's a connection here or a junction, we can't say that. What is clearly in series or in parallel in this circuit, these two here, we see that these two are clearly in parallel. Okay. Yeah, maybe the drawing, but maybe but in the end, since you didn't consider the line, maybe the calculations are correct in the end. So maybe. Okay, let me just.
We have that line, we can like put together another thing with that one.
So like the
Okay, again.
Every time that you got that line, you can like put another part together with that one.
No, because remember that for the case of either series or parallel, this thing that we have here is a junction. So remember the analogies we made about series. Something in series is that there's a connection that isn't being interrupted. So if I were walking a path between C1, 2, 3, and C5, the path is being interrupted here. So that's why it's clearly not in series. And it's not in parallel because to be in parallel, remember the holding hands. Both of the terminals have to be connected to both of the terminals of the other. Okay.
So in other words, series are very picky when it comes to junctions and parallel are not.
Series, if there's any junction in between the elements, it's not in series. It has to be a closed path.
The parallel to the C4, is that
C4.
C4? C4 has a junction going up. You can either go up to C5 or right to C6.
And the key here,
So
because, yeah, the key here that they are parallel is that both terminals are joined with both terminals.
But not, so like C4 is not taking with like C5.
No, it doesn't matter in that case. And so this would still be C1, 2, 3. I'm getting out of breath. And this would be C4, 6. Now C4, these two here, that's 6. These two here would be in series. And this would give us then C1, 2, 3 and C5, 6. And here's maybe where the confusion was, because if we didn't draw these lines here, then it automatically looks like it might be in series. So these two would be in parallel. And that would give us the C1, 2, 5. I'm missing 4, right? Yeah. Yep. This would be C4, 6, 5. And this. Oh, okay. That's
Or it doesn't matter.
it doesn't matter, but let me just to be congruent. It doesn't matter because it's still in the same point, but let's draw it like it was over here. Either way, it's equivalent, but this would be here. And this one would be C1, 2, 3, 4, 6, 5, which would be the total capacitance. Okay. So let's finish this one up with the calculations, just so we're in sync here. So give me the calculations for, I'm going to write them down here on the bottom in orange. Give me the value of C1, 2. Those two are in series. So 2.05 times 10 to the minus 6. Okay. Please, let's everybody verify the calculations just so we have them here on the slide. Okay. And then we've got C1, 2, 3, that's in series. So that's going to be an addition. So that would be 2 plus 8, 10.
10.058 times 10 to the minus 6.
Correct. Perfect. Then C4 and 6, that's a parallel as well. And so that would be 0.75 plus 15. It would be 15.75 times 10 to the minus 6. And then C4, 6, 5 is going to be the series of these two. So we have to do the reciprocal. 1.36 times 10 to the minus 6. Please verify.
Yes, I already have that.
Okay, perfect. And lastly, we're going to have these two in series. So C total, that I'm sorry, in parallel. So that's going to be the addition. It would be 16. No, 7.
1.14.
It's 5 farads, which would be 1.14.
Or 11.4.
or 11 point,
11.4.
11
Times 10 to the minus
Sí, lo quieres hacer con microphone.
times 10 to the-
Okay. But both of these are to the -6, the 1.36 and the 1575. Oh, yeah. So sorry, I was looking at the other, yeah, that's correct. Which would be, I'm gonna write it as microfarads. Yep. I was looking at the other 1.11.4 times 10 to the -6. Just to have everything in farads. Microfarads, correct. Screenshot of this. I'm gonna see if I can have the, I'm gonna see if I can get this.
Se suma 0,1, 0,3. ¿Y es este? Más. O sea, más estos y luego- Ah, pero me dio buen punto.
Yes. It was achieved. I got to the point, I don't know if you've heard about dad sneezes.
Yes.
Yeah, I got to that point where
And
I.
also,
Aunt sneezes,
Are those
louder?
aunt sneezes.
Are aunt sneezes louder than dad sneezes?
Yeah,
or-
higher pitch.
They
Higher
are
pitch.
different.
Higher pitch. Yeah, I got to the point where I sneeze in the whole building. Okay, questions with this one?
No.
I got to thinking about this. This is my favorite. This is my favorite handkerchief because my daughter, my mother is teaching my daughter how to. So I don't know.
Like embroidery.
Yeah, so she likes rainbows. So this is not necessarily the rainbow flag, but she likes rainbows, so she put the rainbow flag. And this is a heart that says "I love you, Daddy." And I love this handkerchief, and I have it with me because it's hers. But then I'm thinking, this is something very nice that she gave me, and I'm basically sneezing with it.
Like you
So-
are using it for a purpose. Yes.
Yeah, but I try to sneeze on the part that's not embroidered.
Not the I love you.
Not the I love you part. Because
It's like if your daughter gave you a mouse. Like,
a literal mouse?
no, it's because my brother made a drawing on the mouse pad.
The mouse pad,
And then it became all ugly
Ah.
because my dad used it, but.
Yeah. The same thing happens. I've got the drawings of my daughter here and they're all faded, but yeah. Okay, so I'm gonna upload to Blackboard or put a note in Blackboard. You guys are gonna have a homework task with some exercises. So the next two exercises are gonna be homework task exercises, which are exercises 5 and 6 that are in the PowerPoint. But I'm gonna write those down in Blackboard so you specifically know what the homework task is, because there's gonna be other exercises added as well. We're gonna have this homework task be for when we come back from spring break on Monday. That way we have chance on Monday to review it before the exam. Okay. Okay, I'm gonna clear the drawings here then. Okay. So we're gonna talk a little bit about another important concept, which is basically the energy that's stored in a capacitor. And actually, the energy stored in the capacitor, that's a relatively simple concept. The energy stored in a capacitor, remembering that voltage by itself, voltage is the energy required for a unit charge to move a charge from infinity to a certain point. So voltage is joules divided by charge, or energy divided by charge. And so it's very simple to make a relationship where we say that if voltage is energy divided by charge, then from here we can have that energy is voltage multiplied by charge. And we also know that charge is equal to capacitance times voltage. So with these expressions, we can make a combination of expressions that have to do with or mathematical representation that have to do with the energy in a capacitor based on the parameters. So I can represent the energy in the capacitor based on the voltage, based on the capacitance, based on the charge, and I can know how much energy is stored in it. Now, why is energy stored in a capacitor important? Because one thing is the charge. One thing is the charge or the voltage. But remember that energy is being able to, or it's the potential to move something or create a movement of something. And so there's many applications for that. So does anybody know what a defibrillator is?
Yes, I want to get electric shocks in the hospital.
Exactly, in the hospital or in emergency situations on the field, right? I hope that, have any of you had to be defibrillated before? I hope not. I'm imagining it's not a pleasant. I don't know if I've had to be
I've seen it in
defibrillated.
Grey's Anatomy.
I don't remember. I actually almost died once and I don't remember what happened there. And so I don't know if I was defibrillated or not, but fortunately my life was saved, but I don't know if I was defibrillated. I don't know. But I imagine it's not a pleasant experience. But basically what's happening with a defibrillator, you've heard the term and you've seen it in movies or whatever with it. We charge the defibrillator and then somebody does this and then somebody says clear and boom. So it's not, usually it's not like you just grab the defibrillator. You've heard that procedure. It's not like, okay, here we go, boom. It's always, okay, charge, ready, boom. There's always a time we have to wait for it to charge. Okay. Well, basically a defibrillator is a device that has a battery and it has a capacitor. And when we say we're going to be charging the defibrillator, it's basically we're turning on the battery and we're filling up a capacitor. Okay. The paddles, imagine that the paddles are the connection to the capacitor. And so when the capacitor is filled up, we're basically touching those paddles or touching those two sides of the capacitor to something. And what's going to be happening with the charge or the energy of the capacitor? It's going to go through the paddles to whoever or whatever it's connected. Right. So again, what's happening is that it's a battery with a certain voltage. We're charging a capacitor. Once the capacitor is filled up and charged, we're giving that charge to something else. Okay. Very, very quickly, very easy. Some of you might be asking, or none of you might be asking yourselves, well, why do we need the capacitor? Just grab the battery and put it to the person. Why don't? What's the difference? Think about it. Why do we need to do that? Why do we need to do a defibrillation for a person? What situation does that happen? Why the heart stops and we need an electrical shock to make the heart start beating again. So again, what I just explained is that I have a capacitor. And remember that the capacitor is the sandwich, it's the container. And so I'm filling up the container. And then it has to do with that. I'm filling up the container and then I'm touching the container so that charge goes into the person instantly. Why don't I just connect the battery to the person? It's too much and the battery isn't going to stop. The battery isn't going to stop. I've got a battery and I connect it to you, Estrella. What the battery is just going to be giving you, it's not going to be instantaneous. The battery is a continuous source of energy. So, well, if there's somebody that the heart stopped on the road and you don't have a defibrillator and you open your car and say, I'm going to do a, well, try to revive them, but that's obviously not the, the best procedure, you might kill the person. Why? Because the battery is a continuous flow of energy. And by the way, the battery is gonna have a certain voltage or a certain energy. That's not necessarily the voltage and the energy that we want to get the person. Okay?
It's like
It's
giving them a dose.
It's like, exactly, because it's like giving them a dose of the energy that's very quickly. Remember what we mentioned, that capacitors are like containers, right? And imagine that I have a water container, like one that Cosamis has, and then I just pop a hole into it, and then it's gonna start draining. Depending on the size of the hole and the pressure is how fast it's gonna drain. The same thing with the capacitor. The capacitor is gonna be a temporary battery for the defibrillator. And the moment I touch it to the person, it's gonna discharge at a certain rate. And the idea is that that discharge should be very, very quick. Okay? Is that clear? Let's look at an example. Clear this. Remember that all of this information is in the PowerPoints. So let's talk about this. We've got a heart defibrillator that delivers 400 joules of energy. That's the energy that's required. That's the discharge that we're giving the person. For a capacitor that's charged to 10,000 volts, that's a huge amount of voltage. That's not the amount of voltage that you're gonna have in your car battery or anything like that. So what is the value of the capacitance? So that defibrillator, what size of capacitor does it have to be able to give out 400 joules of energy when it has 10,000 volts connected to it? Okay, so joules. Joules are the units for energy. Pronounced joules like joules. Units for energy. So let's identify the variables that we have here. First off, the energy in the capacitor. I'm going to call that, what color should I use? I'm going to use an orange. I'm going to say that U is the energy that's stored in the capacitor, and that's 400 joules. The voltage, I don't want to use, I'm going to use, excuse me?
U is charged.
No, U, we're going to use U. Usually U is used to represent energy. And usually the U is used to represent potential energy. U is for potential energy.
Can you repeat that?
The U usually in these, when we're talking about energy, U is usually used to represent or talk about energy.
Is it also used as a unit for joules, or is joules have something?
No, joules is a unit for energy. Is a unit for energy. Work times force times distance. So why am I conflicted with regards to colors? I'm going to say that U is the energy, and this is going to be 400 joules. And the voltage that's being applied to the capacitor is 10,000 volts. That's why those things are dangerous. That's why it's, usually the clear is because you don't want anybody to be close to the body or touching the body, because that discharge is going to go through you as well. So usually, again, that's why it's a procedure. Charge, ready, clear. And the clear is because everybody step back. So the question here is, what is the value of the capacitor or the capacitance for this defibrillator? So I've got 10,000 volts, and in the end, I want to give 400 joules. What would be the charge? What would be the value of the capacitance that can be able to generate that energy? Well, we've got some expressions in the previous slide that can help us out with that. I'm going to go back here for a moment. And we know that we can use, what do we have? We have the energy. We have the energy, we have the voltage. And we are looking for the capacitance. So we can actually use this expression that we have here, okay? And I'm going to write that one down here on the bottom, okay? So we know that U is equal to 1/2 of capacitance times voltage squared. Whoops, let me put that over here. Oops. U is equal to 1/2 of the capacitance voltage squared. If we bring out the capacitance, we have that the capacitance is equal to 2 times U divided by the voltage squared. So with the values we have, we can find the value of the capacitance. We know that the energy is 400 joules. And the voltage is 10,000 volts squared. So what is the value of the capacitor for that defibrillator? Eight times 10 to the minus 6. 8 times 10 to the minus 6 farads. That would be 8 microfarads. Let me check my notes here. This is interesting. This could be either interesting or kind of, it's interesting or pathetic at the same time. This is my writing. This is my writing now that I spent, I don't know how much money on that tablet. And this is my writing. And last year, I always ask the students for feedback. What do you think about the class? What could be better? And last year, before I had my tablet, all of the students said, you know what, you're writing with the mouse. It's extremely slow. They were really nice and they didn't say it was extremely ugly, but they were saying that it was very slow. So if I wanted to write that down, I was writing it with the mouse and it was really, really slow. And they said that I should get better at that. And so, which ones? I actually don't remember if it was specifically you guys for the electricity and magnetism. It was, I do remember the control engineer. No, you didn't take it, but it was that group. It was the control engineering students, the mechatronics and the cybernetic students. Yeah, yeah, it was them. And so that was. I'm not sure. Sure about that. I know a few industrial engineers, and this was, well, it wasn't that ugly. It wasn't that bad. But the only thing, but notice that that my daughter writes better zeros than this. It looks like a child, and it took me a lot of time to write this. But it's the same solution. But yeah, this is a wonderful pad. I really enjoy it. It looks better. So at least the feedback was accepted as corrected as much as possible.
Professor, how do you know where to put the?
No, that's actually the good. I experimented with a few tablets, and the first one that I was recommended, I exactly had that problem. It was a tablet that didn't have an absolute, I'm sorry, it had an absolute reference. So the problem was if you did this, You didn't exactly know which part of the screen you were in?
I've been wondering since the first time I saw, like, how do you know where you're?
No, actually, this one is very interesting because it's got the marks here. So the moment I put it close, the cursor appears with regards to a reference. I don't even have to touch it. And so I can write here and something that's different from this one, from the other ones,
You know where the point is.
you know where the point is. In the other one, the point was with regards to the tablet. So that was really bothersome because, and the other curious thing about this tablet is that notice if I do, oh, where's the, oh, okay, if I do this, this is a normal line, but if I do this, I'm actually pressing it like I'm pressing a normal pen. So I can write very lightly, or I can write. So it's very sensible to the touch. And no, I'm really in love with this tablet. So question with that looks like a horror movie or something like that. Right? I should have used better. Was questions with this one. Then. So remember the heart defibrillator example when we're talking. This is actually more. So we were talking about equivalent capacitances and all that, and that's important. But the application of these, I think, is important as well. Now, by the way, going back to the series and parallel and all that, this is the value of the capacitance I need, 8 microfarads. But actually, what we're going to see in reality is that you're not necessarily going to be able to go online and say, give me an 8 microfarad capacitor. Actually, capacitances, resistors, and all that, the components, have certain specific values. So you might find 1 microfarad capacitors or 10 microfarad capacitors, but you might not find an 8 microfarad capacitor. So how could we build an 8 microfarad capacitor using other capacitors with an array of series and parallel? So it doesn't necessarily mean that inside this device there's 1 capacitor. There might be many capacitors, and the equivalent capacitance is this value that that we have here. Okay, so we're going to be doing some examples with the defibrillator. Okay, questions with this one? No. Okay. Okay.
What is
Okay, so let's do some examples. I'm going to be doing there's 5 examples. I'm going to be doing 2 of these, and 3 are going to be for part of the homework. So basically, the homework class is going to be similar to last learning modules. The homework class is going to have about 5 problems, but those problems are going to be kind of a representation of what can be in the exam. Okay, which are really very direct. The problems from this learning module are very direct. So let's look at problem number 2. That's it. Notice, and again, please, you guys, it's really important for you guys to try to, or I'm doing as best as possible for us to relate these things to real life. And I think situation number 2 is interesting. In the previous situation, you notice that the defibrillator that was in the example, it's a portable defibrillator. It's like a situation, yes, these little paddles that an EMT can have on the field. And so notice the situation there. So if I have a heart attack right now, again, I'm not open, I mean, my heart is enclosed in my body. I'm going to need a certain charge to be able to, or we need a certain energy to be able to create the heart to start beating. But notice this situation. If we have open heart surgery, meaning the heart is open and it's exposed, and the person suddenly goes into shock, we also need to do a defibrillation. Yeah, the paddles are, it's different. It's not this, you're not gonna grab the other paddle and put them in the heart.
I was thinking of that.
You kind of squash the heart. They're different. And also the amount of energy is probably not, you're probably not gonna need the same amount of energy. And so that's what this situation is for. It says in open heart surgery, a much smaller amount of energy will defibrillate the heart. So in the previous situation, we had 10,000 volts providing 400 joules of energy to an 8 microfarad capacitor. Now, if it's open heart surgery, we've got the voltage is going to be to an 8 microfarad capacitor. What voltage would need to be applied if we need to provide 40 joules of energy? Okay, and what is the amount of the stored charge? So let's think about that one. Let me open up the canvas here. Whiteboard. Where's the whiteboard? We're going to do of those 5 exercises. I'm going to be doing 2 of them here, and the others are going to be homework tasks. And I'm going to upload what the homework task is later today or early tomorrow. So it says that in open heart surgery, the voltage is going to be, we're looking for the voltage for an 8 microfarad capacitor. So assuming that the capacitor is the same size as the previous situation, but now we're trying to transmit 40 joules of energy. So let's write down those parameters. First is that the capacitance in this case is going to be the same 8 microfarads. So it's going to be 8 times 10 to the minus 6 farads. The energy is going to be 40 joules. It's not going to be 400. And we are looking for the voltage that needs to be supplied. And we're also looking for the charge. The charge. So going back to the previous slide we had, there's a few expressions that we can use, and I'm going to write them down here on the slide here. So we know that energy in a capacitor can be 1/2 of the charge squared divided by the capacitance. Energy can also be equal to 1/2 of the charge times the voltage. And energy can also be one half of V squared. Okay. Okay. So we can find the voltage. We've got the capacitance. We know the energy. And so the voltage, we can use this one to find the voltage. The voltage is going to be 2 times U divided by C square root. If I grab this expression and solve for the voltage. And so this is going to be equal to the square root of 2 times 40 joules divided by 8 times 10 to the minus 6 farads. And that's going to give me the voltage. Okay. Please do that calculation. And the other thing that I'm looking for is the charge. So I can use 3,100. volts, okay? So in the original one, we needed 10,000 volts. Now we need 1/3 of that to be able approximately. And in this case, we can find the charge. The charge can, if we're from the values we have, is going to be equal to 1/2 of Q squared divided by U. I'm sorry. Q is going to be the square root of 2 UC.
You can use the second formula.
Yes, since we already found the voltage, we could also use that one. Yeah, that's correct.
The voltage is 300,162.
That's what Enya got. Let's verify. Yeah, and that's just going to be 2 times 40 joules times
It's a V or a U?
it's a U. U. See, my writing didn't get that much better
No,
since
it's
last
not.
year. No,
I'm
it
sorry.
it got kind of pointy at the
Uh-huh.
bottom. Yeah, square root of 2 times 40 joules times 8 times 10 to the minus 6 farads. And so Q, what value did you guys get of Q? 0.025 without a multiplier?
0.0250. No, without.
These would be, sorry, yes, coulombs. Now, another, so what Andrea observed is also important. Since we already had the voltage, we could have used the second formula as well to find the charge. That would have been valid. And there's actually another formula that we can use, and I'm just going to write it down here. Remember that there's a relationship between the charge, the capacitance, and the voltage. This is also another expression that's part of our toolkit. I'll write this one down. Yep. I'm not gonna erase it yet. Don't worry. I just want to write this one down. Q equals CV. That's the formula that relates charge and capacitance, voltage, and charge. Okay. Questions with this one? This would be problem number 2. Okay. Questions with this one? Okay, I'll see you guys on today, Wednesday, Friday.